Hi, I'm Gregory Green. Today I'm going to be talking about deep potential, which is a framework for recovering the gravitational potential of a system from a snapshot of phase space. I'm at the Max Planck Institute for Astronomy in Heidelberg, Germany. My collaborator, Yuan-Sen Ting, is at the Institute for Advanced Study in Princeton, New Jersey. The overall goal of this project is to be able to map out the mass of a system, such as the Milky Way galaxy, using the kinematics of its stars. Just to give some context to this project, in 2013, the European Space Agency launched Gaia, which is a space telescope which has traveled to a point called L2 along a line from the Sun to the Earth, where it is now orbiting, and carrying out a precision survey of the positions and velocities of over 1 billion stars in the Milky Way. This has given us really the clearest picture we've ever had of the kinematics of stars in the Milky Way, and is allowing us to map with unprecedented accuracy the structure, dynamics, and the mass of the Milky Way. What you see here is a video of the projected motion of the stars over the next few 100,000 years based on velocities measured by Gaia. Before I can talk about how to turn these stellar positions and velocities into a map of the potential of the galaxy, I need to give a little bit of physics background. The first concept that I would like to introduce is phase space. Phase space refers to both the position and the velocity of a particle. We can combine these two different coordinates into one coordinate, which we call the phase space position. Here, we're going to call positions x and velocities v. The path that a particle takes through phase space is determined by the dynamics of the system. In a gravitational system, the accelerations of the particles are given by the gradient of the gravitational field. The gravitational field itself is related to the density of matter throughout space. Thus, if we could measure the accelerations of stars, we could actually directly measure the gravitational field and therefore the distribution of matter throughout the Milky Way. Unfortunately, it's currently beyond our technical capabilities to measure accelerations of stars directly. All we have is a snapshot of the positions and velocities of stars at one point in time. In order to actually learn anything about the gravitational field from this snapshot, we have to make an additional assumption. The assumption that we're going to make here is that the system is stationary. That is, that the statistics of the system are not changing in time. Let's consider now not just one particle, but rather an entire ensemble of particles. These particles are moving through phase space, and we can draw a box in phase space and look at how many particles are entering or leaving at any given time. If the number of particles in the box remains constant, then we say the system is stationary. If the number of particles in the box is not constant, as we see in this example, then the system is said to be non-stationary. We can define what's called the distribution function, which is the density of points in phase space that is both position and velocity. A system is stationary if everywhere in phase space the distribution function is constant with time. For a gravitational system, the change in time of the distribution function is given by what's called the collisionless Boltzmann equation, which you see here. This equation links the change in the distribution function to the gradient of the potential and the gradients of the distribution function both in space and velocity. Now let's say that we knew the distribution function at a given point in time, but we didn't know the potential. We could use a collisionless Boltzmann equation to try to find the potential which would render the distribution function stationary. In the simple example I'm showing here, if we make the gravity too weak, the system will fly apart. If we make the gravity too strong, the system will collapse. However, if we make the gravity just right, the system will continue on in the same state forever. Even though the individual particles are moving, the ensemble of particles looks similar over time. Now with this physics background, I'll show how deep potential uses deep learning tools to measure the gravitational potential of a system. We begin with a set of observed points in phase space. We fit a normalizing flow to these points to obtain a smooth and differentiable representation of the distribution function. The differentiability of this representation is key because, as we have seen, the collisionless Boltzmann equation contains gradients of the distribution function both with respect to position and velocity. We now draw a large set of phase space points from the normalizing flow, and at each point we calculate the gradients both with respect to position and velocity. These gradients will be used later when solving the collisionless Boltzmann equation. Next, we represent the potential using a multi-layer perceptron, that is, a simple feed-forward neural network. We can then calculate gradients of the potential at the same points that we drew from the distribution function. By plugging all the gradients into the collisionless Boltzmann equation, we can see if the distribution function would be stationary. We then update the potential until its gradients render the distribution function stationary. Thus, we are able to infer the potential from a snapshot of phase space using the stationarity assumption. In our paper, we applied this method to mock data from a simple system, the Plummer sphere, and we show that we are able to recover the potential to high fidelity. We look forward to applying this method to real positions and velocities of stars in our galaxy as measured by the Gaia Space Telescope, which will allow us to map out the gravitational potential and the mass of the Milky Way.